Okay, so let's look at some examples for week 13. So the manager of an automobile dealership is considering a new bonus plan designed to increase sales volume. Currently, the mean sales volume is 14 automobiles per month. The manager wants to conduct a research study to see whether the new bonus plan increases sales volume. To collect data on the plan, a sample of sales personnel will be allowed to sell under the new bonus plan for a 1-month period. Now, Part A, develop the null and alternative hypotheses most appropriate for this situation. B, comment on the conclusion when H naught, the null hypothesis, cannot be rejected, and then comment on the conclusion when H naught can be rejected. So really the key here is the 14 automobiles per month. So that's what the current sales volume is. And what we want to do is we want to find out if the new plan will increase it to greater than 14. So that's going to be our research hypothesis. And that's usually how we set up our alternative hypothesis, HA. So our HA is going to be mu is going to be greater than 14. And then the null hypothesis is always just the opposite of that. So it's going to be less than or equal to 14. Now remember, the null always has to include the equals. So if it's less than, also has to be less than or equal to, or it can be just equal to, or it can be greater than or equal to. There can never be an equals in the alternative hypothesis. Now, comment on the conclusion when it cannot be rejected. Well, there's no statistical evidence that the new bonus plan increases the sales volume is one case when you cannot be rejected. And when can it be rejected? Well, when the research hypothesis that mu is greater than 14 is supported. So we can conclude that the new bonus plan increases the mean sales volume. And we'll look at these two in detail more on other problems on how you actually can find the statistical evidence. All right, suppose a new production method will be implemented if a hypothesis test supports the conclusion that the new method reduces the mean operating cost per hour. A, state the appropriate null and alternative hypotheses if the mean cost for the current production method is $220 per hour. What is a type 1 error for this situation? What are the consequences of making this error? And C, what is a type 2 error in this situation and what are the consequences of making this error? So here the key is the $220 per hour. Okay, so what we want to do is reduce the mean operating cost from that. So we want our alternative hypothesis to be less than that value. So that's what we're going to set as the alternative. And then the null is going to be greater than or equal to the 220. Okay, now type 1, type 2 errors. Well, let's look and see what are type 1 and type 2 errors. Type 1 error is when we reject H naught when H naught is actually true. And type 2 is we accept H naught when the alternative hypothesis is actually true. So type 1 error in this situation, okay, so we're going to reject H naught. So we're going to say that the alternative hypothesis, we're claiming that when the new method does not actually lower cost. We're saying it's true, but it doesn't actually lower the cost. So a mistake would be implementing the new method when it doesn't help. Now, type 2 would be when we accept the null hypothesis when the method would actually lower the cost. So the alternative is actually true. Now, this could lead us not to implement a method that would actually lower our costs. Now, in a study titled How Undergraduate Students Use Credit Cards, it was reported that the undergraduate students have a mean credit card balance of $3,173. So that's a key number there. This figure was an all-time high and had increased 44% over the previous 5 years. Assume that a current study is being conducted to determine if it can be concluded that the mean credit card balance for the undergraduate students has continued to increase compared to the April 2009 report. Based on previous studies, use a population standard deviation sigma equals 1,000. So we need to state the null and alternative hypotheses, find what is the p-value for a sample of 180 undergraduate students with a sample mean credit card balance of $3,325, and then using a 0.05 level of significance, what is our conclusion? All right, so our credit card balance used to be $3,173, and we want to know if it's increased or not. So that would be our alternative hypothesis, is mu greater than $3,173. The opposite of that is just going to be less than or equal to, so that's going to be our null. Now this is an upper tailed test, and so we're really looking at the value up here. So what we need to do is we need to find the test statistic first. So we take x bar minus mu naught divided by sigma divided by the square root of n. X bar, that's going to be our mean of 3325. Mu naught was the 3173. Sigma, they told us, was 1000, and there was 180 undergrad students. So we plug that in our calculator, we get 2.04. Now, if we look in the table for z-scores, that comes out to be a 0.9793. And since we want the upper tail test, that 0.9793 is the area over here, and we want the area up here, so we have to take 1 minus that, and that's going to be 0.0207. Now, since we're using a 0.05 level of significance, since our p-value is less than that 0.05, we're going to reject H0. So that means the current population mean credit card balance for undergraduate students has increased compared to the previous all-time high of 3,173 reported in April 2009. CCN and ACT Media provided a television channel targeted to individuals waiting in supermarket checkout lines. The channel showed news, short features, and advertisements. The length of the program was based on the assumption that the population mean time a shopper stands in a supermarket checkout line is 8 minutes. So that's a key number there. Now, a sample of actual waiting times will be used to test this assumption and determine whether actual mean waiting time differs from this standard. So we need to formulate the hypotheses for this application. B, we need to, with a sample of 120 shoppers, showed a sample mean waiting time of 8.4 minutes. Assume a population standard deviation of sigma equals 3.2 minutes, and what is the p-value? At alpha equals 0.05, what is your conclusion? And then compute a 95% confidence interval for the population mean, and does it support your conclusion? All right, so we want to know if this is equal to 8 minutes or not. So our null hypothesis is going to be mu equals 8. Then our alternative has to be mu does not equal 8, because the opposite of equals is not equals. Now we have 120 shoppers, a sample mean waiting time of 8.4 minutes and sigma of 3.2. So we plug all that into our z equation, and we have the 8.4 minus the 8, which is our mu here, divided by the 3.2, divided by the square root of 120. That comes out of 1.37. All right, so that's going to be up here. Now, because z is greater than 0 and this is a two-tailed test, what we're going to do is we're going to have to take 2 times the upper tail area. So using our normal table again with z equals 1.37, that gives us 0.9147. So if we take 1 minus that value times 2, we get 0.1706 for our p-value. Now that p-value is greater than our alpha value of 0.05, so we do not reject H0. So we cannot conclude that the population mean waiting time differs from 8 minutes in this case. At the 0.05 level, that's the key. At this level, we cannot reject it. Now maybe if we was at a different level, we might reject it. So it really all depends on what level you're at here. All right, so now we need to compute the 95% confidence interval. So that's using the equation x bar plus or minus z alpha over 2 times sigma divided by the square root of n. Well, z alpha over 2 for a 95% confidence interval is going to give us a z of a value of 1.96. Everything else we know, that's 8.4. The 3.2 is sigma. 120 was n. So that gives us 8.4 plus or minus 0.57. That gives us 7.83 to 8.97 for our confidence interval. Now, does it support our conclusion? Yes, it does. We can't reject it because 8 is within this region. So since 8 is within that region, we cannot reject it. So we could have done this calculation 2 ways, the critical value way, or even using our confidence interval method. All right, Jones Nursery specializes in custom designed landscaping for residential areas. The estimated labor cost associated with a particular landscaping proposal is based on the number of plantings of trees, shrubs, and so on to be used for the project. For cost estimating purposes, managers use 2 hours, so that's a key here, of labor time for the planting of a medium-sized tree. Actual times from a sample of 10 plantings during the past month follow in times and hours. So that gives us 10 different times. Now with a 0.05 level of significance, our alpha, test to see whether the mean tree sampling time differs from 2 hours. So we need to state the null and alternative hypothesis, compute the sample mean, compute the sample standard deviation, because here they're not giving us the population standard deviation, so the sigma is unknown here. And then what is the p-value and what is your conclusion? So since sigma is unknown, we're going to use the t and not the z critical value. So first, let's do our hypotheses. We want to use 2 hours. So in this case, a lot of I seem to have picked are all the two-tailed tests. So this one again is mu is equal to 2 for the null and mu does not equal 2 for the alternative. Now we can just plug this into our calculator or Excel or whatever, come up with this sample mean of 2.2 and sample standard deviation of 0.516. So either one of those can be found in Excel or your calculator or whatever you have. Now the t value we're going to look at is again basically the same as the z, except now we're using the sample standard deviation. So it's just 2.2 minus the 2 divided by the 0.516 divided by the square root of 10, which is 1.22. Now we have to use the t table, and so degrees of freedom n is equal, or the degrees of freedom is n minus 1 is equal to 9. Now, because t is greater than 0, the p-value is going to be 2 times the upper tail because we have a two-tailed test. Now, if we look at our t-table, which is over here, we see that 1.22, if we look all around on the degrees of freedom of 9, 1.22 falls between here. So really, we can't find what the actual value is here. So we actually have to use a p-value calculator for a student t-test. All right. So, and that tells us we have 0.2535. Now, there's the rest of my page is gone. Now, so that's the exact value. Before we just knew it was between 0.2 and 0.4, but now with that p-value calculator for a student t-test, we know it's 0.2535. And so what does that tell us? Well, the p is actually greater than our 0.05 level of significance, so we cannot reject H naught, and so there's no reason to change from the 2 hours for cost estimating purposes. Okay, so that's going to be our conclusion for this problem. Now, according to the University of Nevada Center for Logistics Management, 6% of all merchandise sold in the United States gets returned. A Houston department store sampled 80 items sold in January and found that 12 of the items were returned. Construct a point estimate of the proportion of items returned for the population sales transactions at the Houston store. So proportion, remember, is going to be the number divided by the total, so the 12 divided by 80. Construct a 95% confidence interval for the proportion of returns at the Houston store. And C is the proportion of returns at the Houston store significantly different from the returns for the nation as a whole. Provide statistical support for your answer. So again, the point estimate here is just the 12 divided by 80, which is the 0.15. Now we're going to use the proportion confidence interval equation, which is just the p bar plus or minus z alpha over 2 times the square root of p bar times 1 minus p bar over n. And this can be calculated because we have our p bar is 0.15, so it's 0.15 times 1 minus 0.15 or 0.85 divided by the n, which was 80 samples. That gives us 0.0399. Now, we can plug in everything else we know. Z alpha over 2 for 95% confidence interval is 1.96, and we had the p-bar as 0.15. So now we have everything here, simplify it, and we get a 0.0718 to 0.2282 for our confidence interval. Now, is the proportion of returns significantly different from the returns as a nation as a whole? Well, as a whole, 6% of all merchandise was returned. So that's going to be our null hypothesis, mu, or not mu, in this case it's p because we're doing proportions. P is going to be equal to 0.06, and that's down here. And then the alternative hypothesis, p does not equal 0.6. And with p equals 0.15, we can find the z value. That's just going to be the 0.15 minus the 0.06 divided by 0.06 times 1 minus 0.0, or 1 minus 0.06, or the 0.94, and all over n. So that's 3.38. Now, if you remember the z-table, it goes from -3 to +3, so that greater than 3 in the table means it's going to be 1, and 1 minus 1 is going to give us 0, and so the p-value is approximately 0 in this case. So we can conclude that the return rate for Houston store is different than the U.S. national return rate because we reject H0, and so the alternative hypothesis is what we find here. All right, so the next one, Young Adult Magazine states that the following hypotheses about the mean age of its subscribers. So the mu is equal to 28 for the null and mu not equal to 28 for the alternative. What would it mean to make a type 2 error in this situation? So I brought the table back over here in case we forgot that type 2 is we accept H0 when HA is actually true. Now, the population standard deviation is assumed known at sigma equals 6 years and the sample size is 100. With alpha equal to 0.05, what is the probability of accepting H0 for mu equal to 26, 27, 29, and 30? So here you need to see page 420 for the steps that we're actually going to be following. And then what is the power at mu equals 26? What does this result tell you? All right, so A, what would it mean to make a type 2 error in this situation? Type 2 is we're accepting that mu is equal to 28 when it actually is not equal to 28. So basically accept H0 and conclude the mean average was 28 when it was actually not. Now we're going to be doing step 2 on that page 420. So if you look at step 2, it says use the level of significance alpha and the critical value approach to determine the critical value and the rejection rule for the test. So since we're doing 0.05, then our z is going to be reject H0 if z is less than or equal to negative 1.96, or z is greater than 1.96. So we want it to be outside of the range. So if I can maybe draw a picture, maybe not. Draw a picture. So we have our negative 1.96 over here and the positive 1.96 over here. So that's going to be, if it's less than that, we're going to reject it, or if it's greater than that, we're going to reject it. So step 3, what does it say? It says use the rejection rule to solve for the value of the sample mean corresponding to the critical value of the test statistic. So this is our equation we're using. Now we plug everything in that we know. We know the z's, positive and negative 1.96. So for negative 1.96, we plug that in, and everything else we have here, we have x minus the 28 divided by the sigma of 6 divided by the square root of n, which is 100. And we solve for the x bar, which gives us 26.82. Now if we plug in a positive 1.96 here and solve for x bar, we get x bar is 29.18. So our decision rule is we're going to accept H0 if x bar is greater than the 26.82 but less than 29.18. So it's kind of the interval there. But we're going to reject it if it's outside of that. So that's going to be this part up here. We're going to reject it if it's outside of this interval. And so we're going to be if x is less than or equal to 26.82, so beyond this, or if it's going to be greater than the 29.18. So now step 5 says use the sampling distribution of x bar for a value of mu satisfying the alternative hypothesis and the acceptance region from step 4 to compute the probability that the sample mean will be in the acceptance region. This probability is the probability of making a type 2 error at the chosen value of mu. All right, so we have to do this for 4 different mu's, 26, 27, 29, and 30. So at 26, we're solving for z, so we have the lower end, we have 26.82 minus 26 divided by the sigma of 6 divided by the square root of 100, which is 1.37. If we look that up in our table, that's 0.9147, but we need to take 1 minus that to get it the region we need. And so that gives us a probability of 0.0853. So that's our B, okay? Our beta, rather, I should say. And for mu equals 27, we plug everything in, we get a negative 0.3, and look that up in the table, that's going to be 0.3821, and beta there is 0.6179. If we plug in 29, we get a positive 0.3, and that's going to be just 0.6179 because we're on the other side now of the mean, because we have the lower and the upper. So we're kind of, now we switch from the lower, now we're going to the upper part. Now at 30, we have the 29.18 minus 30. That gives us a negative 1.37, and that gives us a 0.0853. So if you look, it's kind of pretty symmetric here. At the 30 is 0.0853, the 26 is 0.0853, and then the 27 and 29 are both 0.6179. Now, the last one was, what is the power at mu equal 26? Well, this is what we're needing here, 0.0853. And what does this result tell us? Well, the power is just 1 minus the beta, and beta we said was 0.0853, so that's going to be 0.9147. So when mu is equal to 26, there is a 0.9147 probability that the test will correctly reject the null hypothesis that mu is equal to 28. All right, so let's do, I think this is the last one. Young Adult Magazine states the following hypotheses about the mean age of its subscribers. H0, mu equals 28, HA, mu is not equal to 28. Okay. Now, if the manager conducting the test will permit a 0.15 probability of making a type 2 error when the true mean age is 29, what sample size should be selected? Assume, again, sigma is 6 and a 0.05 level of significance. So at the mu naught equals to 28, alpha a 0.05, now we're going to be using equation 9.7, and this is kind of that note at the bottom there, and it's talking about instead of z alpha, you're going to use z alpha over 2, and so then that gives us 1.96. Now at alpha, alpha equal 29, beta is the 0.15. That's coming up here. So we need to find z of 0.15. And in Excel, if you use the norm .s.in parenthesis 0.815 or 0.85, that's because we know that this is the probability is going to be the greater than, so that's this one. And so we need the area to the left, so that's the 0.85. So that will give us this value of 1.04 here. Once we get that z, that's where that z is. Now we know sigma is equal to 6, and now we just need to use this nice equation to find the number. And so we have z alpha over 2 is 1.96, z of beta is 1.04. Take those two, add them together, square it, times the sigma squared, which is 6 squared, divided by mu naught minus mu alpha, and that's all squared, and so 28 minus 29. Simplify that and round to the next upper number, and we get 324. So I forget what I got with the number, but let's say it's 323 point even, let's say it's 0.01. Even with a 0.01, you want to round up to the 24, because anything over that 23 is going to change all the rest of the stuff if you don't use the 324. So if you rounded down to 323, you won't get the values up here that you need to have, and so you always have to round up. Okay, so that's all I have. I hope it helps.